All right, hello everyone. In this video, I'm just going to give a brief overview of our acids and bases unit. So in our acids and bases unit, we can start off by asking, well, what is a solution? In a solution, you have a solute and a solvent. Your solute is what is being dissolved. What is being dissolved? And then your solvent is doing the dissolving. That's what is doing the dissolving, and in reagents chemistry, this is usually water. All right, so the amount of solute can be expressed in terms of concentration. It's just the amount of solute per solvent, and this is also known as molarity. So you're going to see that a lot throughout this packet. When a solution is diluted, we can calculate the new concentration or the new molarity using the formula. That's M1V1 equals M2V2. So M1, I should say, is the molarity of the initial or the molarity of the initial solution. V1 is the volume of the initial solution, and then M2 and V2 are the molarity and the volume of the new solution. So in our example problem here, it says how many milliliters of 12 molar hydrochloric acid must be diluted to a concentration of 0.75 molarity and a volume of 5. So we're going to plug in some of these numbers into the formula. So our initial molarity is 12, and it's asking how many milliliters. So our V1 is our unknown. This is equal to our new concentration, which is 0.75 molarity, and that's multiplied by the new volume, which is 5. All right, so we have essentially 12x. Multiplying these two numbers together over here gives you 3.75. And so x is going to be equal to 0.3125 liters. However, it did ask for it in milliliters, so we have to multiply this number by 1,000 because there's 1,000 milliliters in a liter, and so we would get roughly 313 milliliters for that one. All right, so different solutes dissolve in different ways. When water is the solvent, ionic compounds, which are made up of a metal and a nonmetal, these will dissociate, which basically means they're going to break apart into their ions once they're dissolved in that water. So for example, NaCl, when it's added to water, will break apart into its ions. So sodium will have a +1 charge because it's giving away 1 electron. And this is aqueous, meaning it's dissolved in water. Plus Cl-. So chlorine takes an electron that's negatively charged. It's going to have a minus sign. And it's also going to be aqueous. All right, MgCl2 is going to break apart into its ions as well because we have a metal and a nonmetal. So you'll end up with Mg2+, because it's giving away 2 electrons this time. Now there's also 2 chlorines, so this 2 becomes a coefficient out front. You're left with 2 chlorines, and these are both dissolved in water, so they're both aqueous. The last one is calcium hydroxide. So, calcium gives away 2 electrons, so it's going to have a +2 charge. It's dissolving in water, so that's aqueous. Plus, we have 2 hydroxide ions. That hydroxide stays together because it's a polyatomic ion, so that stays as OH-. There's also 2 of them, though, in this formula, so we just put a 2 out front, and that's going to be aqueous. All right, ionic compounds that generate hydroxide ions, just like our calcium hydroxide over here, these are known as Arrhenius bases. So this is where we get into the acids and bases of the unit. So this is an Arrhenius base. And so what you're going to learn later on is that there are strong and weak acids and bases. The strong bases are essentially when you have group 1 or group 2 ions combined with a hydroxide. Those are going to be your strong bases. Okay, now let's talk about acids. So molecular or covalent compounds made of, remember these are a nonmetal plus a nonmetal. They can dissolve, but they won't break apart. Now the exceptions to this are your Arrhenius acids, which break apart in a process called ionization. So similar to dissociation, except ionization is when molecular or covalent compounds will break apart. Now, typically covalent compounds don't break apart when they dissolve, but again, the exception to that are acids. So HCl, this is hydrochloric acid, so this will break apart into H+, that's aqueous, plus Cl-, which is also aqueous. This one is sulfuric acid, so the H's will break off of this, and there's 2 of them, so we're left with 2H+, again that's aqueous, plus SO4, and this has a 2- charge. That is also aqueous. Now C6H12O6, this is not an acid. You can typically recognize an acid because it has a hydrogen out in front of the formula. This is just a simple sugar. And so when we write this as it being dissolved in water, it's not going to break apart because it's not an acid. So you can rewrite it as C6H12O6 and then just aqueous at the end. CH3OH, again, this is just a covalent compound. It's not going to break apart. So you would rewrite this as CH3OH and then aqueous. But again, it's not ionizing when it's placed into water. All right, so some acids will completely ionize. That means every single molecule in the solution is going to break apart, or every single acid molecule. And then these are known as the strong acids. Now, I remember this by the saying, and I didn't make this up, so I can't take credit, but it's I brought clue, not sorry if you're thinking about board games. And so your 5 strong acids are HI, HBr, so those are hydroiodic acid and hydrobromic acid. You also have HCl, it's hydrochloric acid. You have HNO3, that's nitric acid. And then the last one is H2SO4, so that is sulfuric acid. And so these atoms that the hydrogens are all bonded to, that's where you get the acronym over here. All right, so other acids are known as weak acids. Basically, if it's not strong, it's going to be a weak acid. This means that some of them will ionize in the solution and some will not. And so the more molecules that ionize, the stronger the acid. So an example of a weak acid would be hydrofluoric acid, so that would be HF. Now, HF, when you put it into water, 2 things can happen. One, it's either going to break apart and form H hydrogen ions and F- ions, but because it's a weak acid, not every single one of these HFs will break apart, and so it could just stay as aqueous HF and not break apart. So the main difference between your strong and your weak acids is that strong acids, every single one of these will break apart into its ions. However, with your weak acids, some of them will stay together and then some of them will break apart. All right. So acids and bases are known as electrolytes. When acids and bases break apart, they form positive and negative ions, and you can see that up here with some of our examples. So HF, if it breaks apart, it can form a positive hydrogen ion and a negative fluoride ion. Now, when they break apart, these positive and negative, the charged particles, they can allow the solution to conduct electricity. All right, solutions that don't break apart in solution will not conduct electricity. So something like C6H12O6, or even CH3OH, these do not conduct electricity because they don't break apart. They're not acids or bases, and they're not ionic compounds, so they're not going to break apart. However, HCl, when it's placed in water, it'll break apart into H+, Cl-, and so when you have positive and negative ions floating around in a solution, that will allow it to conduct electricity. All right, adding a solute to a solvent, so this would be like adding salts or sugar, whatever, to a solvent, will also change that solvent's freezing and boiling points. So freezing and boiling points. We call this freezing point depression and boiling point elevation. Freezing point depression just means that your freezing point is lower than normal. All right, so for example, water, or H2O, normally freezes at 0 degrees Celsius, but if you were to add something like salt, or let salt dissolve in that water, it depends on how much you add, but we could say it freezes at, and again, this is just an example. Now it could freeze at something like -2 degrees Celsius, so it's going to take a little bit longer for it to freeze. Boiling point elevation, it's the exact opposite. So now boiling point is higher than normal. All right, so again, for example, water normally boils at 100 degrees Celsius. Once you add a solute to that water, you let like salt or sugar dissolve in it, it's going to take more time or more energy for it to boil. And so now it could boil at, something like 102 or 103. And again, it depends on how much of that solute you add. So the number of particles in solution affects these changes in freezing and boiling point. So an example question here we have is, what occurs as sodium chloride dissolves in water? So this is an ionic compound, so it's going to break apart or dissociate into Na+ and Cl- ions. So right away, your number of ions are going to increase. So A and B, it's not going to be either one of those because the number of ions will increase. And the freezing point, because you're adding something to that water, the freezing point will become lower than what it normally is. So the answer to this one should be C. Which solution containing 1 mole of solute and 1,000 grams of water has the highest boiling point? So again, the number of ions in the solution will affect how high the boiling point can reach. So potassium hydroxide, this does break apart and form ions. This forms K plus OH minus. So that's 2 ions in solution. This does not break apart, so this would only be 1 ion. So it can't be B because A has more. C, this is an ionic compound, so it's going to break apart into Mg plus OH. However, there's 2 OHs there, so it's going to be 2 OH minus ions. And so this is 3 ions in solution. So that means it's not going to be A because C has more. Now, it looks like D can break apart into a lot of things. However, this is a covalent compound, so it's not going to break apart at all. So this would actually be one, and I should say molecule, not ion. So this also wouldn't be ion. This would be one molecule in solution. So the answer to this one would be choice C. All right, now let's talk about the Bronsted-Lowry base theory, or acid-base theory, versus the Arrhenius acid-base theory. So I usually make this chart. So we have our theories. Both of them talk about acids. Both of them talk about bases. So let's just make a little chart here. Okay, so we have the Arrhenius theory. And we have the Bronsted-Lowry theory. All right, now an Arrhenius acid provides H+ ions in solution. So for example, HCl, this is an Arrhenius acid because you dissolve it in water, you get H+, Cl-. So these H+ ions are indicative of an acid. Now a Bronsted-Lowry acid, it's the same thing. So it's going to provide, we also say donate, H+ ions in solution. So again, something like HCl, this breaks apart into H+ and Cl-, and so these H+ ions, they tell you that you have an acid. All right, now for the bases, an Arrhenius base, and this is where the main difference is, provides OH- ions. So something like NaOH will break apart into Na+ and OH-. So these OH- ions tell you that you have an Arrhenius base. Bronsted-Lowry theory has a different definition of a base, and this says that bases accept H+ ions. So an example, the most common example probably of a Bronsted-Lowry base would be something like NH3, because it can accept a proton or a hydrogen ion to form NH4. And that would be NH4+. So that's the main difference between Arrhenius and Bronsted-Lowry theory. It's really just about those bases. All right, now you can't really talk about acids and bases without talking about pH. So the pH scale runs from 0 to 14. Now, even though it does run from 0 to 14, you can have pHs outside of this range. So it's possible to have a pH of like 0.5 or like negative. You could have a negative pH if it's really acidic. You could have a pH higher than 14 if it's really basic. So a pH that's less than 7 means that your solution is acidic. And just going back up to this chart up here, look at the Arrhenius acids and bases. So Arrhenius acids provide H+, Arrhenius bases provide OH-. So if you have an acidic solution, you're going to have more acid than base, and so your H+ is going to be much higher than your OH- concentration. So we'll put a greater than symbol there. Now a pH of greater than 7 means that you have a basic solution. And so here your hydroxide ion concentration is going to greatly outweigh your hydrogen ion concentration. So we'll have a little less than symbol over there. A pH equal to 7 means that you have a neutral solution, and your H+ and OH concentrations are going to be equal to one another. All right, so what does the P in pH actually mean? The P in pH actually just means negative log, so it's like a function. This means we can calculate pH using the formula. pH is equal to the negative log. Now don't be scared by the log because it's really more of like a formula here. So it's really just the negative log of the hydrogen ion concentration. All right, so let's just do an example here. So if the concentration of H3O plus is 1 times 10 to the negative fifth, is the solution acidic, basic, or neutral? Well, we have to solve for the pH. So pH is equal to the negative log. Now, H plus and H3O plus, they're essentially the same thing. So it doesn't matter which one you're plugging in there. So the negative log of H3O plus is going to be negative log of 1 times 10 to the negative fifth. And that's going to be equal to 5. So our pH is equal to 5. This means it's less than 7, and so we have an acidic solution. Now, if the concentration of H3O plus is 1 times 10 to the negative 7, we'll do the same thing here. So we take the negative log of 1.0 times 10 to the minus 7, and that's going to be equal to 7. So if our pH is 7, that means we have a neutral solution. All right. If the pH value of a sample has 100 times fewer hydronium ions, so hydronium is that H3O plus, and if you have less of that, fewer hydronium means you have a less acidic solution. So less than an equal volume of a vinegar sample with a pH of 3. Now, the pH scale is on a log scale, meaning when you change the pH by 1, the hydrogen ion concentration is actually changing by a factor of 10. So when you have a pH of 3, when you go to a pH of 4, you're getting 10 times less acidic. That means when you're going to a pH of 5, so if we go from a pH of 3 to a pH of 5, we're getting 100 times less acidic. So for this one, the answer would be a pH of 5 because it has 100 times fewer hydronium ions. All right, so the strength of an acid affects the overall pH of a solution. So given the two solutions, we have 0.1 molarity hydrochloric acid. So that's our concentration of our acid. And then we have 0.1 molarity HF. So which solution has a greater concentration of H plus ions? Now you might be tempted to say that these have the same pH because they have the same concentration. However, remember, HCl is one of our strong acids. So this means every single one of them breaks apart. So all of them break apart. Now HF is a weak acid. So not all of them break apart or ionize. Okay, so because HCl is a strong acid and all of them break apart, and HF is a weak acid, this means that the HCl will have a lower pH, that means more acidic, than the HF solution. And that's because it's a strong acid. So not every one of those HF molecules will dissociate, or ionize, sorry. All right, now calculate the pH values for both solutions given in the previous question. So for calculating pH, pH is equal to the negative log, and we have to do this for both solutions. So let's just do the HCl first. Now the concentration of hydrochloric acid is 0.1 molarity, and since every single one of those molecules will break apart, that means you'll have the same concentration of H+. So we take the negative log of 0.1. So that means we'll have a pH of 1 for the HCl. Now this problem says that the H+ concentration in the HF solution, hydrofluoric solution, will be going to be the negative log of 7.9 times 10 to the minus 3. And so that means we have a pH of 2.1. So our hydrochloric acid is going to have a lower pH by about a factor of 10 than the hydrofluoric solution. All right, so what can we use to determine pH? In table M in your reference table, you have some common acid-base indicators. So again, these are just chemicals that will change color based on their environment, based on the pH of their environment. So looking at an example problem here, it says one sample of a solution with a pH of 10. So this is going to be basic. Is tested with phenolphthalein. So let's look up at table M. So here's phenolphthalein. It has a range of 8 to 9. This means when it's greater than 9, it's going to be pink. When the pH of its environment is less than 8, it's going to appear colorless. So if you have a pH of 10, it's going to appear pink. And then another sample of a solution is tested with litmus. So litmus has a range of 4.5 to 8.3. If you have a pH of 10, that's greater than 8.3, so this would appear blue. And so phenolphthalein is pink, and the litmus is blue. Then that means this would be choice A. All right. So what happens when you mix an acid and a base? Mixing an acid and a base results in what is called a neutralization reaction. That's neutralization. And these are all double replacement reactions. Double replacement reactions. Okay, so let's look at an example of a neutralization reaction. So we have HCl, this is our acid, NaOH, this is our base. HCl breaks apart into H plus and Cl minus. NaOH breaks apart into Na plus and OH minus. Now in a double replacement reactions, your positive ions just switch places. And so in doing that, you are left with NaCl plus HOH. And if you notice, HOH is the same thing as H2O. So anytime you have a neutralization reaction, your products will be some kind of ionic compound or a salt plus water. All right, so let's look at this next one. So MgOH2 breaks apart into Mg2 plus and 2 OH minus ions, or hydroxide ions. HF can break apart. Remember, not all of them will, but some of them will break apart into H plus and F minus. Now, if this is being neutralized, your positive ions will switch places. So this means we have, again, HOH plus MgF. Now, remember, your charges do want to stay neutral. So Mg has a 2 plus charge, and F has a 1 minus charge. So in order to make those equal 0, we need 2 fluorines to make those charges add up to 0. Now, this is not balanced, so in order to balance it, we have 2 fluorines on the right side, only 1 fluorine on the left. So I'm going to put a 2 in front of that HF. However, we also have 2 OHs and only 1 OH on this side. There's also 2 H's now and only 1 H on this side. So I'm going to put a 2 in front of that. And so your final reaction would result in 2 molecules of H2O and 1 MgF2. All right. Next one says an acid is added to a beaker containing sodium hydroxide. So remember, sodium hydroxide will break apart into Na and OH minus. So what happens to the number of Na plus and OH minus ions in the beaker? Okay, so let's draw a beaker. We have our NaOH. So we're going to add this to the beaker. Once you add it, you have Na plus and OH minus ions kind of floating around in that solution. Now, if you have, and it doesn't matter what acid it is, because all acids are going to donate H plus. So if we put H plus into this beaker, what'll happen is the Na will kind of just hang around, not do anything. However, the OH minus and the H plus can combine to form water, or H2O. So you're left with H2O and Na plus ions kind of floating around in there. And so the number of Na plus ions stays the same. So Na plus stays the same, but look at and see what happens to the OH minus ions. So the OH minus, you start off with some in there. However, in the new beaker, we don't have any OH minus. So hydroxide, your hydroxide ion concentration will decrease. All right, finally, the titration equations. So the formula used for titration equations is MAVA, which means the molarity of the acid times the volume of the acid, and that's multiplied by the number of hydrogen ions. Next we have MBVB, so that's the molarity of the base times the volume of the base times the number of hydroxide ions in there. Okay, so the first question says a 2 milliliter sample of NaOH solution is exactly neutralized by 4 milliliters of 3.0 molar HCl solution. All right, so let's kind of extract some of the data here. So we have HCl, 3 molarity, 4 milliliters. This is your acid side. NaOH is a base. We have 2 milliliters. We don't have the concentration. It also says what is the concentration of the NaOH, so that's going to be what we're solving for. And this is your base. So for the acid side of the solution, we have 3 molarity times the volume, so that's 4 milliliters, and the number of H plus ions. HCl breaks apart into H plus and Cl minus. There's only one H plus ion there, so you just put a 1 there. The molarity of the base, this is what we're solving for, so that's going to be our X. The volume of the base is 2 milliliters. Now it doesn't matter if you have milliliters or liters, you just have to make sure they're the same. So as long as those units are the same, that's fine. And NaOH breaks apart into Na plus and OH minus. There's only one OH minus, so we put a 1 here. Okay, and so solving this out, we're left with 12 is equal to 2x. That means 6 is equal to x. So what does that mean? Our concentration of the base is going to be 6 for the molarity. 6 molar sodium hydroxide. All right, one last question here. So in a titration, again, that's what all these formulas are on, we have 18.21 milliliters of 3 molar sodium hydroxide. So right away, that's going on the side of your base. They're added to an Erlenmeyer flask. So if we draw out an Erlenmeyer flask containing 25 milliliters of HCl. So we have HCl, and we're adding NaOH. 3 drops of phenolphthalein. So that's typically what you use when you're trying to figure out if something's become neutralized. They're added until 1 drop of NaOH turn the solution a light pink color. So essentially you're just adding sodium hydroxide into this beaker until it just barely turns pink. That means it's going to be neutralized. And all we're really doing here is calculating the molarity of the HCl. Okay, so let's pull out some of this information here. So the formula is MaVa times the number of hydrogen ions is equal to MbVb times the number of hydroxide ions. So for our basic side, we have 3.00 molarity times 18.21 milliliters. NaOH only releases 1 hydroxide, and so this is going to be 1. Now for the acid side, hydrochloric acid only produces 1 hydrogen ion. That's multiplied by the volume, which was 25. And then we're solving for X over here. So we're solving for the molarity. So we're left with 25X is equal to 54.63, and then X is equal to 2.19 as your molarity.